Hi students, welcome to my lectures on thermodynamics. In today's lecture, we are going to discuss about the last topic in the enthalpy. Okay, the last topic here is adiabatic reaction. And the adiabatic reaction conditions is of one of the most important aspects in thermodynamics. For example, if you ever see a welding and a welding work, people used to light up the acetylene gas, okay, and you can see the flame is coming out of during the welding process, and people use the concept of adiabatic flame temperature because to melt any particular metal you need to produce very high amount of energy and requires high temperature. So using the thermodynamic concepts that we can able to find out what is the maximum flame temperature. Okay, these are the specific examples of adiabatic flame temperatures. And second thing is, knowing the maximum possible temperature can allow us to design any reactor. Because if you don't know what is the maximum temperature, if there is some mistake happened in the industry, because of that the temperature has been raised because of some reaction. So what is the maximum possible raise in the temperature can be estimated using the concepts of adiabatic reaction conditions. So in the today's example, let us find out that how to use the concept of enthalpy in determining the maximum possible temperature in an exothermic reaction. For example, let us go to the board. There is a reactor in which a specific reaction is happening. The reaction, you can assume, CO plus 2H2 gives rise to CH3OH. So the reactants are entering at initial temperature T0 and exiting at temperature and at a T. Okay, the reactor is adiabatic, means we are not allowing any heat to go in or any heat to come out during this reactor. Okay, that during this travel in the reactor there is no exchange of heat in the system. Okay, if that is the case, okay, what is the maximum possible temperature it can raise because of this reaction? That is what the adiabatic temperature. T is the maximum possible temperature that can happen because of this adiabatic conditions inside the reactor. So let us assume we can using this picturization the concept. Imagine adiabatic condition means the change in enthalpy equal to 0 before and after reaction. If you calculate the before enthalpy and after enthalpy, the delta H will be equal to 0. That is what the adiabatic conditions. Change in enthalpy equal to 0. Imagine this is our state 1, this is our state 2. When the reaction, example, an exothermic reaction is happening in the reactor, that will take the reactants from 25 degrees centigrade to some higher temperature of the product, which is at temp T. Okay, the objective is to find out this maximum possible temperature in this adiabatic reactor systems. And let us assume the process happens from state 1 to state 2 in a adiabatic conditions. That means low temperature to a maximum and high temperature. During this process, the enthalpy equal to change in enthalpy equal to 0. That is what this adiabatic conditions is. We have to find out what is this T. But inside this reactor, we don't know how the process conditions, how the temperature is, how the pressure is. During this process, we cannot able to find out what is the exact change in enthalpy conditions. Okay, so if you don't know the actual path in which the reaction is happened, we can able to travel another route to find out this temperature, because the enthalpy are the state functions. That means the enthalpy depends on initial state and final state. It doesn't matter whether you have gone through this path or this path. So that is what the beauty of the properties, thermodynamic properties. Thermodynamic properties like enthalpy, it depends on initial and final stage. It doesn't matter how it has gone to the final state. So let us take that as an advantage to find out this maximum possible temperature. So I am starting my reaction at 25 degrees centigrade. So that is why I marked at initial temperature is 25 degrees centigrade. I will conduct because I don't know what is this actual route. The best possible method is conduct the reaction at room temperature and increase the product temperature to T. Because I have the information of change in enthalpy of the reaction at 298.15 Kelvin. That means I know something about the enthalpy of the reaction at 25 degrees centigrade. So let us conduct the reaction at 25 degrees centigrade. Once you finish the reaction, increase the product temperature from T0 to T. So this is enthalpy of the reaction, this is enthalpy of the cooling, which is equal to the enthalpy of this particular adiabatic reaction. So that is what it is written here. The change in enthalpy, okay, it is nothing but the change in the reaction, enthalpy of the reaction plus enthalpy of the heating. Okay, we know because the adiabatic conditions, the change in enthalpy is equal to 0. So in place of delta H, I put 0, which is equal to enthalpy of reaction at 298.15 Kelvin plus enthalpy of heating of the products. In other case, 0 equal to, I know enthalpy of heating or cooling, the formula is N into integral Cp dt. This is what we normally use when the heating and cooling process. So which one you are trying to heat? After conducting of the reaction, only the 100% assume that 100% reaction is happened. That means after this reaction only CH3OH will be present, CO and hydrogen will be absent. So after the reaction, you have to increase the CH3OH from T0 to T. That is why here we have considered only CH3OH, not CO and hydrogen. So as it's a regular process, okay, multiply and divide by R at this expression, bring one R to inside the expression. That is what that is happened. And if you follow my previous lectures, this particular term integral T0 to T Cp by R is nothing but ICPH. Okay, ICPH of CH3OH. Okay, what is this ICPH? Is nothing but MCPH into T minus T0. This MCPH of CH3OH. So if you rearrange this equation, objective is to find out the temperature T. So keep T on the left hand side, remaining the terms on the right hand side. So you get the final expression. Using this expression, you can able to find out what is the exit temperature, that is maximum possible temperature in this adiabatic conditions. That means you should know enthalpy of the reaction, you should know how many moles of CH3OH is present, you should know R, you should know MCPH and T0. What is this MCPH of CH3OH? I mean this is for the CH3OH. A plus B by 2 into T plus T0 plus C by 3 into T square plus T0 square plus T into T0 plus D by T into T0. A, B, C, D are the constants of this CH3OH. So that means you can see, if you know all the terms, you can able to calculate T. If you see only MCPH, MCPH is consisting of T term also. That means as long as you don't know T, you cannot calculate MCPH. As long as you cannot know MCPH, you cannot calculate T. That means because if you know the T, then only you can able to calculate MCPH. But if you don't know T, how can you calculate MCPH here? You know T0, which is the room temperature. What is T? Which is you have to find out. That means in this term, the T term will be there, MCPH. So because you cannot able to find T, if you don't know T, you cannot able to calculate MCPH. What you have to supposed to do is iteration procedure. Assume some value of T, calculate MCPH. If you know MCPH, again calculate T. See, whatever the assumption is matching with that of a reality. If the assumption in this T is nothing with that of an actual T, that means your assumption is wrong. Go for new guess. So this is what the iteration procedure you are supposed to do to find out the final temperature T. So I will explain the iteration procedure also, don't worry. Assume this reaction that is happening in this adiabatic conditions. I know initial temperature, I have to find out T. The moles of CH3OH is 1 mole. I mean, during this heating step, I have to heat this 1 mole, of the product to reach from T0 to T temperature. Because I have assumed initially 1 mole of CO will be present, 2 moles of hydrogen will be present to form 1 mole of CH3OH. Okay, that is why I have written the moles of CH3OH is 1 mole. In this formula, it will be 1. What is this? Standard enthalpy of reaction at 298.15 Kelvin, it is minus 90135 joules. Looking minus means exothermic. Exothermic means after the reaction, the temperature will rise in the adiabatic conditions. R equal to 8.314. A, B, C, D constants of CH3OH is given here. That means you know A, B, C, D of the CH3OH. Let us start the iteration procedure. Step 1. Assume temperature. Okay, let us assume how I have to assume a higher number. Why? Because it's an exothermic reaction. The final temperature will be higher than the initial temperature. So let us start with some 1000. Okay, calculate MCPH using equation 2. That is what estimate MCPH using this equation 2. Now you know the MCPH. Calculate the T using this equation. That means estimate the temperature T using equation 1. That means you can get temperature. Now estimated temperature is 1558.05. You have assumed 1000, you got 1558, which is not matching. That means your assumption is wrong. Go for a new guess. Now let us take this as a guess. Assume that T assume is 1558.05. Again estimate MCPH. Okay, you got 10.03. Again using this T, find out the final temperature 1354.14. You can see T assumption is different than the T calculated. That means it is wrong. You have to go for a new guess. I take this as a new guess. Again I have calculated MCPH. Again I have calculated the T. So in such cases, assumption is 1354.14, calculated is 14.10.69, which is not matching. So if you continue to do this, at some point of time, your assumption will be equal to actual. You can see after you can see MCPH, it is 8.4, now it is 10.9999.6. You can see it is reaching to the steady value. After certain iterations, you can see MCPH value is not changing and the T assumption and T actual is also very close by. That means you have reached to the solution that if you conduct a reaction here at 25 degrees centigrade, this particular reaction in adiabatic conditions, the final temperature after the reaction is 1397.31, right, Kelvin. Okay, this is kelvins, which is equal to 1124 degrees centigrade. That means you have started with as 25, you have reached more than 1000 degrees centigrade after the adiabatic reactor conditions. So this is how, because this is very important, because in the welding stage people use acetylene gas. Acetylene gas, at the flame of the acetylene gas, that means if you see a small flame, okay, this flame of the acetylene gas during the welding, it will reach to more than 3000 degrees centigrade. Okay, that is why it is important to us, because that much temperature is required to melt a metal for the welding process. So using this adiabatic concepts, you can able to find out the maximum possible temperatures for different reactions. This 1000 degrees, that means 1124 degrees centigrade is for this particular reaction. Similarly, you can able to calculate the acetylene gas reaction and find out what is the maximum temperature in the adiabatic case. Okay, thank you very much. And from the next lectures, we are going to go in for the separate concept. See you soon. Thank you.